Welcome back, everyone.
Hi.
Let me introduce our next speaker. Okay, so Dr. Jay Nandy is currently working as a visiting researcher at Google Research India. Before joining Google, he also worked as a research assistant at NUS. His research interests include robustness of deep learning models, predictive uncertainty estimation, unsupervised and weakly supervised learning, and he has published in premier AI conferences. He completed his PhD from the School of Computing at the National University of Singapore in 2021. So let me hand over to our next speaker.
Thanks. So let me share the screen. Is it visible and am I audible?
Yeah, we can see and hear you.
Okay, thanks. Um, so my name is Jay, and thanks for the introduction. And I'll be presenting this work on towards maximizing the representation gap between in-domain and out-of-distribution examples. So this work was done during my PhD from NUS, and let's start. Okay, so deep learning models are shown to be working wonderfully well for different real-world examples, but they have been shown that this model, people have shown that this model produces overconfident prediction, meaning that so when the model has not seen something, when the model has not seen some input which is unknown to the model actually produces very high confidence predictions. So this raises the question: when should we trust and how should we trust the model? And determining the source of uncertainty can actually answer that. Determining allow us to reject some of the samples or manual intervention for sensitive real world applications, and allow us to enhance the reliability of of these models for real world applications. So in this work, I am going to talk about out of distribution detection, focusing on out of distribution detection. So there can be so in terms of predictive uncertainty of DNN, there can be three types of uncertainty. One is model uncertainty, when we cannot effectively determine the model parameters. However, this kind of uncertainty is reducible given enough amount of data. So the network, we cannot identify the network parameters, but if we have infinite amount of data or possibly very large amount of data, we can reduce that uncertainty to almost zero. The other two type of uncertainty occurs due to data. So suppose, for example, here we can see that star, and we can see that three classes and three overlapping classes, and one data point star marked as star. So that data point, even human cannot understand in which class that data point should fall. So that kind of uncertainty is kind of known to the neural network, to any DNN or any machine learning model, but the model cannot correctly put them in the correct class, or there always going to be some uncertainty in putting them into the correct class. The other type of uncertainty is called distributional uncertainty, where the data point is coming far away from the distribution, original in-domain distribution, and the model has no idea how to react on that data point, and that kind of data point we call as out of distribution data point. So our work is going to focus on this out of distribution data point and try to distinguish between in distribution and out of distribution data point. To understand this example more clearly, let's consider this cat versus dog classification model. So, given a neural network, if we train a neural network to distinguish cat and dog, so the neural network can produce very high confidence that this image belongs to a cat, this image belongs to a dog, but this image, it contains both cat and dog. The model should produce some kind of uncertainty. Model should produce like 50% cat, 50% dog, and this is raising the data uncertainty. On the other hand, suppose we get an image of an airplane which is unknown, which is neither cat nor a dog. So in that case, we cannot identify, we cannot say which class model cannot say which class it should fall. And interestingly, it has been shown that instead of producing low confidence, the model actually produces high confidence. For example, the model may say that this is with 99% probability, this is a dog. So this is what we call a distributional uncertainty that raises due to the out of distribution examples. So in this paper, we show that uh, while there exists multiple methods to distinguish the in-domain and in-domain versus out-of-domain examples, we show that they tend to when there is data uncertainty and distribution uncertainty, they tend to produce similar kind of representation, uh, and we cannot distinguish the in-domain versus out-of-domain example. And overall, this leads to compromise their overall OD detection performance. So we propose a technique that we are going to see in detail later, that basically maximizes the representation gap between in-domain and out-of-domain examples. And for that we took a existing framework called DPN framework, and we propose a novel loss function for DPN framework, and we address some limitation of the DPN framework. So what kind of thing we can expect from a neural network when we are going to get some input. So if the input is correctly given to the neural network and correctly, some in-domain example, let's say there are 4 classes, then the neural network is going to produce very high confidence for one of the class if the image or input is coming from some known class. Otherwise, in case of out-of-domain distribution or in-domain misclassification, like misclassification occurs originally due to data uncertainty. So when there is data uncertainty or distributional uncertainty, in general, when we are going to use only one neural network, then they typically produce similar kind of representation. They typically try to produce similar kind of representation among the existing approaches. So we cannot distinguish this in-domain whether the uncertainty is coming due to in-domain misclassification or OD examples. So in the Bayesian approach means there can be like a distribution over the representations, over these representations. Then suppose the simplest Bayesian approach can be a deep ensemble model. So instead of taking output from only one neural network, you train multiple neural network, a set of neural network, and you take the output from there. Now, when we are going to get going to get the output from all these neural network, if the model knows that the input is coming from some in-domain distribution, then they tend to produce similar kind of representation. For all of these neural network are going to produce similar kind of representation, similar kind of probability score. So we are going to get a cluster of probability score, yeah, in this simplex. So simplex means a probability space, and each of these point inside represent one probability score. So for example, in case of cat, dog versus it's a cow, then one point is representing cat, one point is representing dog, and one point is representing cow. So given an image of a cat, the model is all the models are trying to produce with very high confidence that this is an image of a cat. Then we are going to get a cluster of points in this corner, right? Now, if the image contain both all these, sorry, you have any question?
No, I think JV can continue.
So suppose we have in the image, suppose we have cat, dog, cow, all these things. Then the model is again very confident that that it contains all these 3 images. Then the model is going to produce one cluster, a very dense cluster in the middle of the middle of the simplex. So that means like 0.3, 0.3, 0.3 for all the classes, and all the models are going to behave similarly. Now suppose we get an unknown image. Suppose in an event class. Hello. Sorry. So suppose we get an image of an airplane, then we are going to get an outer distribution. Then this is an outer distribution example, and none of this model knows exactly how to proceed, and they going to behave differently. All these models are going to behave differently. So we are going to get a sparse representation in the simplex. Now the problem of this method is that we have to train multiple models, so the training time increases. Also, we need to get representations from all the models, so the inference time is also increased. So basically, computation this technique is computationally expensive in terms of training as well as in terms of inference. So, and also the problem is that we do not have any control over these neural networks, so it becomes very difficult to control their desired behavior. Now, existing Dirichlet distribution, Dirichlet prime network, they try to instead they try to produce from one neural network. They aim to produce one simplex. So, a distribution. Suppose we try to learn a distribution over this simplex that called Dirichlet distribution, which is very, very simple. I will just explain in a bit what is the Dirichlet distribution and all these things. But it essentially what it tries to do is that suppose we have infinite number of classifier, and then we try to put obtain the prediction from all these classifiers. Then all these classifier is essentially going to produce one very peak representation in one corner of the simplex. And for in-domain misclassification, they tend to produce one very sharp representation in the middle of the simplex, and for the outer distribution they tend to produce a flat representation all over the simplex to show this is confident prediction, to show this is misclassification, and this is outer distribution. Now we show that in reality this is not the case, and instead when we are going to misclassify, then the model actually produce a very sparse kind of representation, and this is because of their formulation. We are going to get a very sparse kind of representation. So it becomes difficult to distinguish this representation from this representation. So essentially, we cannot distinguish an image that contains cat, dog, and cow, and that contains an airplane. So what we propose is that instead of producing something like that, what if we shift the distribution? What if we shift the density of the representation to the corner of the simplex, to three top corners of the simplex, essentially going to produce a multimodal distribution. So this is our proposed this is what our proposed method essentially does. So basically, it maximizes the representation gap from confident prediction. We are going to get a flatter representation for misclassified example. Then we are going to get a sharp multimodal representation for OD examples. So I'll come to all these things in one bit. Okay. So what is a Dirichlet distribution? A Dirichlet distribution is basically, suppose we have a k-class classification model. So typically a neural network produces probability scores, right? So all these values, all the output of the model should sum to 1, and the model should have like one large value for the correct class, and for the incorrect class we have small values, right? Now instead of that, a Dirichlet distribution requires to produce some value alpha that is greater than 0, and that's all. So if we are going to get, if we can produce a neural network that for, let's say, for cat, dog, and cow. So suppose we have an image containing cat, dog, and cow, and then the neural network is producing 100, 100, 100 for all these classes. Then we are going to get a very sharp distribution in the middle of the simplex. Suppose we are going to reduce the value from 100, 100, 100 to 10, 10, 10, then we are going to get flatter, and then for 1, 1, 1, we are going to get very flat, sparse representation. Now, if we are going to reduce the distribution, these values, we are going to get in the fractional region, then we are going to get multimodal distribution over the simplex. So that is our desired representation compared to this is the existing method's desired representation. So clearly you can see the representation gap is increased and we can easily detect the in-domain versus OOD. Now, how can we achieve that? So this is typical slight maths about that, but don't worry. I mean, it's just very simple. I'll just try to explain what is this. So we suppose we need to produce a concentration parameter, and remember in the last layer we apply something called softmax classifier. So softmax classifier sorry, softmax activation. So softmax activation takes some logic values. So and we take the exponential of that logic value, right? So this logic value can be negative or positive. When you are going to apply exponential form of that, then you are going to get something like values which is always greater than 0, and that's all we need to produce a Dirichlet distribution. So we take the output, which is real valued output, we apply the exponential, and that is our desired Dirichlet distribution representation. Now, how are we going to design the loss function? The loss function is again very simple. So if we consider the mean of the representation, that mean of the representation is given by this formula, which is the softmax formula. So we take the exponential of the logic values and normalize it by the summation of the exponential of across all the logic values. So this formula is going to determine in which corner we want the distribution to be, and then we are going to produce we are going to correctly scale these values of alpha c's, which is going to determine how sparse the representation, what is the variance of the representation. Right. So again, just one quick reminder. So if we are going to get a sparse unimodal representation, we want to achieve this large precision values. So alpha c's are the precision values. So after getting exponential, whatever we are going to get, these are the precision values. So we are going to get as large precision values for unimodal Dirichlet distribution, and then they should concentrate in only for the correct class, right? And for the when we want to achieve something like this representation, then we want to achieve something like probably we want to produce something like negative logic values that would lead to produce concentration values which is less than 1. Now for this thing we want to produce something like exponential values which should be close to 1. Alpha is close to 1, so these values are going to alpha c's are going to be close to 1, right? Then we are going to produce a sparse representation over this flatter representation over the simplex. Now, how we are going to propose the proposed loss function, how we are going to train the model. So first part is the standard cross entropy loss function, and second part is the modeling the precision value, modeling the alpha c's. First part is going to determine determine the corner of the simplex where we are going to produce the sparse or dense representation, and this part is going to tell us about the value, how the value of alpha c's are going to be. So this is the standard. This part is the standard cross entropy loss function, where it's just y minus of y log of p of y given x, and this part is we take the sigmoid of the logic values. So sigmoid is going to produce is going to scale all these values to positive and negative. So and then we either increase the value or we decrease the value. So for in-domain example, we want to increase the value. So that means we choose lambda in to be very high, always to be very high. And this is going to produce something like this representation. And this part is ensuring that our if we are going to sample one data point from here, we are going to get one high probability score for the correct class and low probability score for the incorrect class. Now, if we want to model an out of distribution example, then we are going to take the cross entropy loss function, and we want to say that the model is equally uniform across all the classes. So we are going to model this by again by cross entropy against uniform distribution versus the probability of output probability of the neural network. So we want an uniform representation over the uniform probability scores over the simplets. And this part is, again, we want to reduce the value. So this part always we choose lambda out to be less than lambda in. Now, if we choose uh, lambda out to be less than lambda in, but it is greater than 0, then we are going to create a flat representation. But if you are going to choose lambda in which is positive and large, and lambda out to be negative, then it enforces the neural network to produce negative logic values for in domain for out of domain examples. So essentially, after applying exponential, we are going to get fractions, and we are going to get multimodal representation across all the at different corner of the of the simplets. So we are going to get this kind of representation, which is essentially going to maximize the representation. Now, the way we can measure the uncertainty, the simplest way of measuring the uncertainty, which if we have single neural network and in the non-Bayesian setting, then we probably can use maximum probability score. So if the classifier, if very high confident for one correct class, we achieve very high probability score. And if the classifier is if the classifier can detect the OD, but it cannot express it is an OD, or detect some uncertainty, but it cannot detect why this uncertainty is coming because of misclassification or outer distribution, then we are going to get a representation like this, which is like uniform across all the classes, right? So in this case, again, we cannot distinguish between misclassified example and OD examples, right? So we need some different kind of measure for DPN models. So the idea of DPN model is as follows. We can so basically we are going to use mutual information. So what is mutual information? So mutual information says that we take the average value, and then we take average representation and take the entropy of that average representation, minus we take the entropy of each of these representation, and then take the average of that. So basically what it means, so if we have one simplex, and then this is very highly confident, then we are going if we are going to take if we are going to compute the first term in this case, then average of these things, average of these samples are going to look like this. All of them are going to be very similar to each other because it's a very sharp representation at one point, unimodal sharp representation. So we are going to get very equal representation from them. And then if we are going to take the average of that, then they are going to look like the same as a single image. And then if you are going to compute the entropy, since there is no there is this representation is very sharp, then the entropy of this term is going to be very low. So our first term become low for this kind of representation. In the second term, what will happen? We are going to take the entropy of each of the distribution. So each of these distribution is very confident. So the entropy is going to be low, and then we take the average of that. Then we are going to get like almost these entropy values are going to be almost close to 0. Then average also going to be almost close to 0. So we want to get a low term and minus a low term. So overall we are going to get something like very close to 0 term for confident prediction. Now in this way, if we analyze for this kind of representation, we are going to get high term and high term. Both first term and second term is going to be high and equally high. Then we are going to get something like almost 0. Overall mutual information is again going to be almost 0. In the third case, we are going to get high, but the second term is not that low. So not that low. I mean, we can just explain this thing because some of if we are going to generate a sample, we may get a sample from here which is very high confident. we are going to get very low entropy, but we may get some data, some sample from here where we are going to get very high entropy. Then the overall of this term is not very high or very low. So it's like average, and then moderately high or moderately low. So we are going to get something like average high, so which is sufficient to distinguish between these two things. But we do not know how sparse this specified representation is. So we may not, in practice, we may not distinguish this in domain versus OD examples. What we propose in the other case, it ensures that all the samples we are going to get, so first term is always going to be high, but we also ensure that all the samples we are going to get is going to be low, because it's sample from the corner, and in all the corner the entropy is the probability scores are going to be very confident for at least one class. So overall, the representation is going to be the each of these entropy of each of these representation is going to be low. So overall, the sum of the average of this representation is going to be low. So basically, we are going to get the first term as high, second term is low, and this term is low. So in terms of metric, we can distinguish this low this in domain examples versus OD example very clearly. So if we look into a synthetic dataset, and the same example we started with, so we have three classes, and for these three classes, if we train a classification model, standard classification models, and suppose we have all these data which can standard classification model which can distinguish between in-domain and OD example, then we are going to get a representation which is correctly classifying, correctly identifying the in-domain example, but it is going to produce almost high, kind of very high uncertainty in the overlapping cases, and also outside the model, outside the in-domain example, they are producing very high representation. So we cannot distinguish this something falling in this middle point and something falling here, and this is the representation when we train our model in our proposed specification. Uh, in the other case, if we try to produce a flatter representation in these two cases, this is the old paper, and this is in our paper, but we choose the hyperparameter as follows. So we call it ppn plus. So in that case, we again see the similar case, and max probability in any cases, max probability cannot distinguish this in domain and OD examples. Now comes to the mutual information. In the mutual information, we can see that our model can very sharply distinguishing this in-domain versus OD examples, and for these other models, it's not so much. So and also we can see that as we are going far away from the in-domain examples, the representation, the uncertainty is actually increasing more and more, and we cannot distinguish this point and this point. Similar thing we can observe for the existing BPN model as well. Now there exists some other technique as well, which is called precision. I'm not going to go in the details. So basically it says that if we take the sum of this alpha c's, then we are going to get. I mean, since we are explicitly increasing the alpha c value, then we are going to get high value in the middle and lower value outside. Similar case we observe here, but in this case, the model is failing to distinguish the in-domain and OD example using this metric as well. So these are the three examples, and finally we show the example on real world cipher 10, cipher 100, and tiny ImageNet dataset, and we show that our model consistently outperforms the existing model. When we are choosing the mutual information as the OD detection metric. So in conclusion, we show that we identify the problem of the existing model, that existing model cannot distinguish the in-domain and OD example correctly. But we propose, by addressing, we address this problem by proposing a new framework where we introduce one regularizer, essentially one regularization, along with the standard neural network training, and it actually become a Bayesian framework, and we can distinguish the in-domain and OD example correctly. And experimentally, we show that our model consistently outperforms the existing OD detection models. So that's all. Thanks.
Hi, Jay. Thanks for the talk. So you have tested this on image data, right?
Yes.
So is this applied for other modalities as well, like for tabular data or language data?
For our case, one limitation of our problem is that we need OD example. We need ample amount of OD example. So for that, probably we may not be able to apply this in tabular dataset. Probably in some cases, if we have explicit OD example, sample of OD example, then we can use this. Otherwise, probably we cannot apply this method. For images, it is very easy. We just choose, we have one classification task, and we just choose some other publicly available dataset and train the model. Then it works. But may not be that easily explicitly applicable for tabular datasets, because tabular dataset has no structure. That's why.
So do you know if there are any other methods that we can apply for tabular data, or like people have not looked at that yet?
I guess, I mean, there exists, like if you take this deep ensemble model, then deep ensemble model can actually, theoretically it should be able to take care of this tabular dataset as well. But I have not seen, I mean, I did not follow that literature very closely till now, but I'm sure there are some work on tabular dataset as well.
Okay.
Where basically you do not need extra data, then you should be fine.
Okay. Thank you so much.
Thanks.
Hi, Jay. I'm Priyanka. Thank you for the nice talk. I have a small question. So when it comes to your method, how does it work with the data that suffers from class imbalance problem? Have you explored that aspect?
Yeah, I did not explore that class imbalance problem, but class imbalance problem is not a concern for us, because if we have in-domain example and OD example, so class imbalance problem occurs in the in-domain example, and our objective is to distinguish the in-domain example from the OD example, right? So I don't think there will be any problem for class imbalance datasets.
Okay, thank you.
Okay, are there any more questions for Jay? Okay, if not, let's thank the speaker. Thank you very much, Jay. So we will meet again in the panel discussion in a little bit.